Watch what happens when you string together a swarm of AI agents and ask them to collaborate on a complex task. Without strict data controls, the nodes rapidly desynchronize. They overwrite each other's work, read from stale data, and the entire system collapses into chaos. The common industry response is to blame context window limits or poor prompt engineering. But the failure of scaling multi-agent systems is an architecture problem. Hardware engineers encountered these exact issues, specifically the risk of processors making decisions based on inconsistent or corrupted shared data, decades ago. They developed the logic to prevent these race conditions in 1984. Approaching an agent swarm as a prompt engineering exercise ignores the underlying data movement problem. To build systems that actually work, we have to look closely at classical computer architecture. Welcome back. I'm the bearded AI guy, and today we are breaking down a position paper from researchers at UC San Diego that analyzes AI memory through the lens of hardware systems. Currently, developers assume that equipping an agent with memory simply means spinning up a vector database and running basic retrieval augmented generation, or RAG. Modern multi-agent frameworks treat memory purely as an input-output mechanism. They pull external data and constantly shuttle it directly into the agent's prompt. This photograph of a dense silicon wafer illustrates the physical reality of the von Neumann bottleneck. AI computation happens incredibly fast, but shuttling data back and forth to external databases creates a traffic jam that dominates both latency and token costs. To clear this traffic jam, developers must stop relying on standard database queries. We need to borrow memory consistency models from classical multiprocessor hardware. As we shift from single-agent chatbots to collaborative swarms, we need strict memory consistency contracts to ensure every agent sees the same version of the truth at the same time. A scalable computing system requires different speeds of memory. An agent needs a fast, immediate workspace to hold active tasks, and a larger, slower filing cabinet for long-term storage. The researchers at UC San Diego formalized this concept into what they call the three-layer agent memory hierarchy. This diagram outlines those exact tiers. Data filters through the I/O layer, down to cache, and rests in memory. The I/O layer handles standard interfaces to ingest external documents. The cache layer provides fast context, separating accessible data from what's actively loaded. OS-inspired frameworks like MEMGPT are already implementing these exact layer boundaries, moving information between tiers so an agent functions far beyond a fixed context window. This tiered approach shows that structural caching is a fundamental necessity for end-to-end data movement. Without it, reasoning degrades the moment information gets stuck in the wrong tier. When multiple agents work on the same file, the system needs strict rules. If one agent updates a plan, the others cannot continue making decisions based on the outdated version. Hardware engineers solve this by separating coherence from consistency. Cache coherence ensures multiple copies of data don't diverge. Memory consistency dictates exactly when and in what order new writes become visible to the rest of the system. The canonical hardware solution for this is an invalidate-based snooping protocol, specifically the MESI Protocol, developed in the 1980s. This diagram illustrates the 4 MESI states used to track cache blocks. When an agent reads a file, the data enters a mutually shared state safely. When one writes a change, the protocol triggers an invalid state in all other copies, forcing a disciplined update. Look at a practical coherence failure. Agent A reads a plan. Agent B simultaneously edits and safes. Agent A finishes its own edits and hits save, silently deleting Agent B's work entirely. In hardware terminology, this is a lost update. If an agent makes a decision based on an old requirement it never saw change, that is a stale read. Classical database theory offers a proven software architecture solution for these anomalies, multi-version concurrency control, or MVCC. Under MVCC, agents do not overwrite a shared object. Instead, writers append a completely new version of the object to the database. Access is strictly managed. Essential directory dictates exactly which agent is permitted to see which version at the exact moment they start their transaction. Implementing version counters and access directories allows concurrent agent reads and writes without destroying the shared logical state of the swarm. The multiprocessor analogy works perfectly until we hit one physical reality. Computer chips process rigid binary states. AI agents process fuzzy, ambiguous language. This creates a semantic gap. Hardware coherence relies on deterministic comparison and exact equality. A silicon cache line has a stable, unambiguous byte address. Natural language does not. A text-based fact admits partial overlaps, paraphrasing, contradictions, and temporal drift. This leads to semantic conflicts. An LLM will readily blend an external contextual fact with its own internal training, breaking the exact equivalence that hardware protocols depend on. The immediate engineering hurdle is definition. Developers must explicitly redefine the unit of coherence for LLMs to make it trackable. The hardware protocol transfers to AI only after you structure raw prose into discrete, versionable artifacts. Cache coherence for agents is leaving the theoretical phase. Recent research has already begun mapping these hardware protocols directly onto LLM systems. A 2026 preprint titled Token Coherence maps MESI cache protocols onto multi-agent LLM systems to minimize synchronization overhead. The researchers built verifiable mechanics, creating invalidate-on-write and fetch-on-demand architectures specifically designed to handle semantic tokens. Modern production LLMs are paving the way for this. Major platforms now utilize conditional prompt caching to reuse computation for stable prefixes and context objects. This reinforces the foundational engineering premise of all cache coherence. You must separate what exists in long-term memory from what is injected into the processor right now. When we treat the prompt as the only site of memory, we hit a scaling wall. Memory hierarchy and consistency protocols are now the primary constraints for building complex agent swarms. Scaling collaborative AI is a strict systems engineering discipline. The blueprints for success were written in the 1980s by multiprocessor architects. If this systems-level breakdown upgraded your mental model of AI architecture, hit subscribe to join the Bearded AI Guy community. Let me know in the comments below how you are handling state synchronization in your own agent swarms right now, and tell me what technical paper we should deconstruct next. Warning tone. If you aren't proactively managing your swarm's cache coherence, you are just waiting for a stale read to ruin your pipeline. I will see you in the next one.